We're going to continue our discussion on differential equations with the discussion on slope fields. Unfortunately, sometimes it's impossible to solve a differential equation in the sense of separate, integrate, give an initial condition, and find an explicit formula for the solution. If you'll remember a few weeks ago when we talked about differential equations, we were guaranteed that when we were asked to solve them, they would be first order separable. Well, here we show that despite the absence of an explicit solution, we can still learn a lot or discover a lot about the solution to a differential equation through a graphical approach, and that's called a slope field. So suppose we were asked to sketch the graph of the solution of this differential equation. Well, everything that we've done before, we were able to separate, get everything in terms of one variable and its with respect to on one side of the equal sign, and the other variable and its with respect to on the opposite side of the equal sign. But clearly here, we're going to have an issue when we try to separate because of this plus sign. So let's just say, for instance, we didn't realize that we couldn't separate and integrate, and so we need to subtract y from both sides. So we would have dy dx minus y equals x, and then we would multiply both sides by dx. So we would have to distribute that dx over this minus sign. That would just leave us with dy here, but it would leave us with y times dx here, and of course we would have x times dx over here. And this would be our clue that it is not separable. We cannot separate and integrate with respect to y on one side and with respect to x on the other side. So when we're in this context, the best that we can hope to do is maybe discern what's happening by looking at the slope field for this differential equation. So we don't know a formula for the solution. We can't separate and integrate. It's not first order separable. So how on earth can we possibly sketch a graph and talk about it graphically? Well, let's think about what the differential equation is, what it means. It's the slopes, it's the derivative, it's the slopes everywhere in terms of x and y. So the equation tells us that the slope at any point xy on the graph, and we'll call that the solution curve, we'll talk more about that in a minute, is equal to the sum of the x and y coordinates at that particular point. So for instance, they want us to draw the graph of the solution curve through this point. So we know that this point lies on the graph of the solution for this differential equation. And because the curve passes through that point, the slope must have an x coordinate of 0 and a y coordinate of 1. So the slope there, dy dx, at the point 0, 1, has to be the sum of the x and y coordinate. So we know at the point in the plane, 0, 1, the slope through that point is a positive 1. And so what we're going to do with a slope field is we're going to draw a small piece of the tangent line through the point. Just a really small piece. Doesn't have to be very big. And so we know that at this one single point in the plane, the curve acts like this, because remember, that's the power of the tangent line. Very near the point of tangency, the equation of the tangent line acts like the curve. So here's what's most powerful, and here's what a slope field does for us. Let's do it at more than one point in the plane. Let's do it at any point that we want to. Now, we already determined that at the point 0, 1, the slope to the curve is 1. So we're going to draw just a little piece of something sloped 1, and I can tell a slope of 1 by kind of determining that's what a slope of 1 would look like. So I'm just going to draw a small piece of it. And now I can draw pieces of the slope field anywhere I want to. Since they want the solution curve through this point, I'm going to take integer points. Those are easiest to work with. And by integer points in the plane, the x-coordinate and the y-coordinate are all integers. That's what I mean by integer points. And all these little crosses here tell me and give me a good idea of where those integer points are. So I'm going to draw several little pieces of the slope right around and see if I can get an idea of how this function is behaving right around the point 0, 1. Well, I know that the slopes everywhere are the sum of the x and y coordinates. So let's just start with this point here. This is a x coordinate of -2. It has a y coordinate of 0. So I know the slope through that point is -2 plus 0. So the slope's -2. Well, I know a negative slope is sloped in this way, and a slope of 2 would be about this. I can tell, you know, down 2 and over 1, the slope through that point would look about like that. Now again, I don't want to draw very much of that tangent line. I'm just going to draw a little piece of it, just enough so that I can tell how the function is behaving. And there it's got a slope of -2. Let's work with the point -1, 0. And the slope through that point is -1 plus 0. So that is a slope of -1. So again, the slope of -1 looks roughly like this. And I'm going to be compared, as you are, with how my slopes are compared with one another. If I call this a slope of -2, then the AP reader is going to look for the fact that I know that this is still a negatively sloped line here, but that it is shallower than my slope of -2. So you're not going to be judged against any standard. You just need to make sure that you can show the AP reader that you recognize if this is a slope of -2, then here's what my slope of -1 would look like. Here's what my slope of +1 would look like. Those are the things that they're going to be looking for. So let's continue to fill out these integer points that we have here. The point 0, 0 is 0 plus 0, so the slope through there is 0. Let's go ahead and figure out what those slopes would be, and then we can fill in the tangent lines. I have the point 1, 0 that has a slope of 1. I have the point 2, 0 that's going to have a positive slope of 2. We'll hop up here and do the point -2, 1. That's going to have a slope of -1. -1, 1 is going to have a slope of 0. We'll jump over here to this point. That's the point 1, 1. That will have a slope of 2. The point 2, 1 will have a slope of 3. Let's hop up here. -2, +2 will have a slope of 0. -1, +2 will have a slope of 1. This is the point 0, 2. That's going to have a slope of +2. Here's the point 1, 2, and that will have a slope of 3. And the point 2, 2 will have a slope of 4. So now that we've got them all, let's try to draw our slope field. At the point 0, 0, this is where we were. At the point 0, 0, the slope is 0. So I'm going to draw a horizontal tangent line through that point. At the point 1, 0, the slope was a +1. So if I called this a +1, they're going to expect that this should look the same. Through the point 2, 0, the slope is 2. And again, I'm going to kind of try to draw it more steeply than my +1 in the positive direction. Let's jump back over here to the point -2, 1. That had a slope of -1. This one has a slope of 0. 1, 1 had a slope of +2, so it should look like this one. 2, 1 had a slope of +3, and that would be even steeper, something like that. Let's go over here. -2, +2 had a slope of 0. -1, +2 had a slope of 1. 0, 2 had a slope of 2. 1, 2 had a slope of 3, so it should look a lot like this one. And then a slope of 4 should be even more steep than my slope of 3. So you get the idea. There's what part of the slope field will look like. And they want us to draw the solution curve through the point 0, 1, this point right here. Well, here's the brilliance of the solution curve in the slope field. We are going to follow, we're going to come right along that little piece of the tangent line, and we're going to come out from it until we hit another tangent line, and then we're just going to follow along what it tells us to do. This one, we come down here and we hit tangent lines that head us back up this way. So I didn't draw enough pieces of tangent lines to get very much of the solution curve, but you get an idea of how you could do it. Just follow the tangent lines, right? They're telling you the slopes everywhere. So now let's have a discussion of what we mean by a slope field, and then what we mean by the solution curve. Because we kind of know what these things are analytically, let's just tie them into what we have found out graphically. The slope field is equivalent to your general solution. Remember, the general solution was the whole family of functions whose slopes were the differential equation you were initially given. So the slope field itself is like the general solution of a differential equation. It just happens to be a differential equation where we cannot analytically separate and integrate and get back to that general solution. And the solution curve itself is based on an initial condition, right? Remember that? Here is the initial condition for your derivative or differential equation. And so once you use that initial condition and actually draw the solution curve, that is equivalent to your particular or exact solution. So we already kind of know a lot about slope fields and solution curves already. It's just some new terminology. So if we're asked to draw a slope field, we're just going to use the differential equation they gave us. We're going to do all the points that they tell us to. Here they didn't tell us which ones to do, we just pick some, but they will tell us which points to use and where to draw your slope field at. So don't worry about that. And then if you're asked to draw the solution curve, then you go to that initial condition and you follow what the slopes are telling you to do. Now I'm going to go to the next slide, and this one's actually been generated by a computer algebra system. So this is the same differential equation. This is still dy dx equals x plus y. But I want to talk about some things because sometimes you're given a slope field and you're asked to match it to a list of differential equations. So we've got some things to consider when we're actually given a slope field. Sometimes we're not even given the solution curve. So the first thing you do, number one, is identify where the tick marks are. Okay, identify tick marks, because that's going to make a difference, and you'll see some examples where that's true. So notice that here, straight up and down, there's a tick mark, there's a tick mark. So there's 4, there's 5. Here's -1, -2, -3, -4, -5. You have to identify all the tick marks. So there they are. And notice that we just did integer points, right? 1, 1, and we did 0, 0, and we did 2, 0, and 2, 1, and so forth. There's a lot more little pieces of slope field here. As a matter of fact, these little pieces are at every half of a tick mark. So there's lots more pieces of slope fields here that we need to pay attention to. So the very first thing you're going to do is identify the tick marks and then look for the overall behavior that the slope field shows you. Here we have some sort of line that we know the functions must travel along, whether they're below that or whether they're above that. So pay attention to what the slopes tell you, and remember, the slope field is the family and the solution curve is the particular solution. Slope field is general solution. So we'll pick this lesson up in the next video.